When you're ready. Okay, can you just make it full screen maybe? Formularfehler gefunden. Das ist nicht gut, okay? Well, okay.
Great. So our second speaker probably needs no introduction. So Alexander Wagner is going to tell us about.
I'll tell you about what you just heard about. Okay, so I had this idea a while back. Actually, we were looking at fluctuations in multi-component systems, and it turned out that I wasn't convinced that Poisson distributions are the way to go, but I also didn't know what was the way to go. So I was looking for some way of actually figuring this out, right? And let's see. There we go, this way. So there's a top-down approach that we just heard in great detail that Matteo told us about, but there's also a bottom-up approach. So these, even the Navier-Stokes equation, are not a ground truth, right? The Boltzmann equation is not a ground truth. It's an approximation to some real physical system, right? And there's no reason that the Boltzmann equation should be our starting point, right? So the Boltzmann equation comes from something, and there's this whole, many of you will know about this whole rigmarole that you go. So you have your Newton's equation, you get a Liouville equation, you get VBTK, you get you cut it off at the lowest level, you make some approximations, which we saw earlier, and you end up with your Boltzmann equation, and then you just go to test the Boltzmann equation. That's one way of going. But what if we could arrive at the Boltzmann equation straight from an MD simulation, right? Rather than going through this whole big apparatus where we threw stuff away which we didn't even know that we threw away. And there we go. There we go. So that's basically the idea, that we have this bottom up. We start from MD, and oops, so we get two of them. Okay, just way too quick. Okay, so the idea is you have an MD simulation, right? And you all know how to do this. You solve Newton's equations for however many particles you have, right? And you can superimpose the lattice on top of this, which are these red lines that you're seeing here, right? And you can just remember which particles. So up there, you take the center part. You can, of course, you do this for every cell, right? You look at these particles, then you iterate this for a certain amount of time, and your particles will end up be somewhere else, right? And in fact, it's really an embarrassingly trivial idea. So now what you do is you say, well, I associate this with the integer lattice gas occupation numbers, right? So I said this particle went in the time step from this cell to this cell. So then the n that goes in this direction is 3, right? And the same for the one up there, and you can just count. And of course, depending on how long your time step is, they'll be able to travel further, right? If you have a very short time step, they'll mostly stay inside, and a few will go over the edges. If you have a very long time step, they'll just disperse around with some kind of Gaussian cloud, right? And if you have a mean velocity, of course, they're drifting along with that velocity as well. But if you are doing a normal lattice Boltzmann simulation, really what you care about is just where are the particles, right? or what are your densities of particles, and what's their momentum. That's really all you care about. And that information is encoded here, right? You have that information from this coarse graining. So once you do this, you obtain first this lattice gas, defined exactly this weight that it has told you. You can write this down mathematically, right? But this is what it is. But then you know the ends at all times, right? You from one time step to the next. You know ends at all times. That means you can deduce what the collision operator is. It's just the difference between ends at different sites and times. And you write down something that looks like a lattice gas evolution equation, right? So this, you have streamed ends are the original ends plus some xi, which is how they got redistributed. Right? So this looks exactly like a lattice gas evolution equation. And then when we take the Boltzmann average of this will be a lattice Boltzmann equation. Right? And you can do this analytically, as we just heard from Matteo, if we assume that this particle displacement is a Gaussian, which is a good approximation in most cases. It might have some advection velocity here. This u delta t is how far it's going to move, right? It has this displacement. Then the width of the Gaussian is just the mean square displacement, something you have to measure. Then you can do this integral that I had there, and you can find out what the Fi is according to this particle displacement, right? And if you're not in equilibrium and it's not a Gaussian, you can still do this very calculation and find out what your Fi are based on this distribution function. Now you've reduced the problem of defining that as Boltzmann to just the problem of finding particle displacement probabilities. They're exactly equivalent. Well, not exactly. From the particle displacement, you can obtain the full lattice Boltzmann model. That information is completely included, and you see what this equilibrium distribution looks like. It has some exponential, some error function in it. And then, of course, as Matteo just showed you, you can compare this. Hello? Maybe you can't. The down arrow or something will work. There we go. Okay. So we see here at u equals 0, exactly the graph that you just saw. And one thing that's very encouraging is because we all know lattice Boltzmann, we know our loved weights, which are these black, red, and blue lines drawn across. Those are the weights. And it turns out that there is this one a squared value, which is the lattice spacing over mean sphere displacement of 1/6. They are in very good agreement. They're not in 100% agreement because there is still stuff here which is not 0, but it's orders of magnitude smaller, right? So there's some small correction, but this is presumably the reason why these lattice Boltzmann weights work so well if you're deriving it from a microscopic approach, right? They just come out. It's not the one you have to choose, but it's one you can choose. Now, of course, you don't have to do it at u equals 0. You can look what happened at other u's. That's what you see here. And compared to the standard quadratic equilibrium distribution, you see there's no difference up to a velocity of 1.1, which is, we all know up to 0.1 is when you get good things. Now, for large velocities, they deviate. And in fact, what happens here is that at 0.5, the rest particles and the moving particles cross because there's no restriction to the velocity set. They're just changing roles, right? If you have a velocity of 1, you get exactly the same distribution as this one, except all the names are moved over by 1, right? So they have to exactly change. So they have to cross exactly at this point, which they do, right? Which is, again, encouraging. And we looked at these distributions, even for these systems that don't even face separated to fancy stuff. If I make them a little denser, so for dilute systems, they look Poisson distributed, which is encouraging because that's what people always assumed. So for dilute systems, things that look more like ideal gases, you get ideal gas statistics, which is great. For denser systems, you kind of know that you don't, right? And you know if you have a dense system, it can't fluctuate as much. So it's compressed. The total density is narrow, as you would expect. However, the Fs are not narrower. The Fs actually widen. The only way you can combine these widened distributions to get a narrow distribution is if they're highly correlated, right? And in fact, you can look at the correlation that they become very large. And you can look at how this scales. And this is this dotted line there is the predicted. So you know that if you take more number of particles, you expect your fluctuation to go down as 1 over square root of n, right? But for dense systems, they don't. It's just wrong. These fluctuations in the ends go down way slower. So these fluctuations don't go away the way we think they should, which is already a cool result, which it got straight out of this mapping molecular dynamics onto this lattice gas, averaging it. Well, we just look at the lattice gas fluctuations here, right? So is there any way we can get rid of this top stuff there? Anyway. Perfect. Nice. Okay. So now, and I think, so you can use this to directly analyze lattice Boltzmann. We could also use that to think differently about lattice Boltzmann. We thought about lattice Boltzmann in the ways of deriving it from lattice gases. We derived it in terms of deriving it from top down, from a Boltzmann discretization. But actually, this allows you to think about it differently, because this is a completely new way of coming up with what a lattice Boltzmann simulation is, right? And that can be really helpful, because suddenly stuff pops up that maybe exists previously, like those weights, but maybe stuff that looks very different from what you expected, like those fluctuations. And so we thought, well, first we can apply this now, because what we get is a lattice gas. Doesn't look like the normal lattice gases, because normal lattice gases that we used from the early FHP, they're Boolean lattice gases. Now, these are not Boolean lattice gases, they're integer lattice gases. And it turns out there isn't a lot of literature on integer lattice gases, so let's just try to derive them from scratch. And we have to define the collision operator, right? And first, of course, we want to have that it's, well, mass conservation is trivial, we just don't destroy any particles. We want it also to conserve momentum. And that's a little tricky, because that doesn't come straight out of the MDLG. The MDLG, the real momentum is conserved, but the particle momentum, the lattice gas momentum is not quite conserved, because imagine a simple case where a single particle moving slowly, right? It will be a rest particle because it sits in the cell, and then it will jump, it'll have a velocity of 1, that will be a rest particle again. So just simply the one particle cannot conserve momentum, but you can show that if you do the average of it, it will be vigorously correct. But instantaneously, it's not. But it's hard to keep track of momentum, so we're going to demand for our model that it conserve momentum. And we've already derived that this equilibrium distribution gives us these lattice Boltzmann weights. So we want to have the right weights at u equals 0. And we want to have the collisions that don't depend on anything except for I'm going to pick two particles, I'm going to collide them. It shouldn't depend on anything but these two particles. So it shouldn't matter what the mean velocity or the total density is. Let's just make it depend on those particles, okay? And that doesn't leave us a lot of freedom. No, nothing wants to do anything anymore. It's doing something again. So all you can do, let's do it the simplest case, D1Q3. The simplest thing we can do, in fact, the only thing we can do, we have rest particles, make them moving particles. You have moving particles colliding and making them rest particles. That's it, right? Nothing else for D1Q3 would conserve momentum. Well, nothing else that does anything, right? You can swap particles, but that's it, right? And you have to find out, you want to have that your average value is giving you these 1, 6, 2/3, 1, 6, right? And you do that by taking two rest particles that are colliding. You always make them, two moving particles, they always become rest particles. You have two rest particles, you make the moving particles with the probability of 1 over 8. And you can convince yourself that that gives you this WI weight that you expect, right? Now, that defines what's the equilibrium look like at u equals 0. But what does the equilibrium look like at different values of u? And what you get is this quantity, which turns out that the probabilities of the NIs is, well, okay. It says that the probability of these NIs will consist of Poisson distributions, products of Poisson distributions, right? So this, I hope you recognize those as Poisson distributions, dependent on this Ni, so they have the Ni factor here and the Ni factorial. This mean value of your Poisson distribution given by this quantity here, this F equilibrium, which turns out to be the same as the entropic lattice Boltzmann, which we didn't put in, it just happens to come out. It's the only equilibrium distribution consistent with this very basic lattice gas. That's what Ilya mentioned very early on in his first talk. This is, you get this very same entropic equilibrium distribution just emerging out of these two very, very simple collision rules, right? So we didn't really do anything fancy. We just put in these very trivial collision rules, very trivial D1, Q3, out pops the entropic equilibrium distribution. And we can now so what we did for the first version is we took two particles and collided them at random. And this is a very consistent way of doing it, but it's a very slow way. Now we can ask, is there any way we can accelerate it? And in fact, what we can do is, yeah, perfect. So if you have a local condition, we have a certain number of total number of particles, total J, right? There's one more degree of freedom, which we call pi. It's the sum of the FIVI, which is free. And what I can end up is a distribution in this pi, and there's the equilibrium value. So there will be an equilibrium distribution of these pi values, and I can sample out of that equilibrium distribution. That's what a full collision. So if I do lots and lots of collision over a long time, I'll end up with this local equilibrium distribution. There's some subtleties about how you obtain it. And with that, you arrive at a collision operator that actually, so this is millions of lattice updates per second on some not very good laptop because it's not very expensive. And this red one is the performance of the entropic lattice Boltzmann without fluctuations. And the black one is the performance of the lattice gas with our sampling collision operator, where we have to obtain the sampling using some nasty recurrent relation, which we know is not optimal. If you pre-calculate your random numbers, you're actually faster than lattice Boltzmann. So there is, I think, a real argument to be made that these methods can be not just toy models, but actually equivalent models computational in terms of computational cost. And what they'll give you is, well, whether you like fluctuations or not, either you'll be plagued with fluctuations or you'll get your fluctuations for free if you want them, right? But it is not like the fluctuations in Boolean lattice gases, because your density is not 1 to 6. Your density can be 100, 1,000, and here you see the average number of particles per cell. So if you have 600 particles per cell, yes, you have fluctuations, but they're not the fluctuations of old, right? They're way lower. And here's just a couple of results that you have. So here, okay, so one thing I didn't say from the last slide, which is that instead of colliding all the particles, we can just select a fraction omega of particles and take those as a new distribution and collide them amongst themselves. And if I do that, it turns out that omega is equivalent to the 1 over tau in lattice Boltzmann. So what we did is we took like a little sine wave, looked at the decay of the sine wave, measured the amplitude, and you can measure that as a function of omega. This is for like 1,000 particles per cell. You get a very good agreement with the lattice Boltzmann. If you look at the viscosity values, there's lattice Boltzmann and lattice gas, and they look like there's one symbol because they're right on top of each other. Turns out there is a small dependence on the density, which, a lattice gas is not lattice Boltzmann. It has some additional features. For instance, if you have no particle, we have on average 1 particle or less per cell, it can't collide. Even if you pick the 1 particle, it has no partner to collide with, right? So there's going to be no collisions. but the more particles you have, the more efficient the collisions will be. So there's a larger number of uncollided particles, or ones that you just couldn't collide, right? Because you couldn't change this. So as your density goes down, your viscosity goes up, which is, of course, what you see in real systems as well. And here is last little statement. So we looked at this, and it turns out that the collision operator, mathematically, you can show it's not exactly the same as it's not unique. Let's put it this way. It actually depends on the distribution of particles that you have. So you have a priority distribution. If this a priority distribution is close to the equilibrium distribution, so if it's also Poisson distributed, then you can show that the collision operator becomes essentially the Lattice-Boltzmann BGK collision operator. And you end up, so we looked here at some, we tried to break the system. So we thought, well, let's try a shock wave. So we have like a thought shock tube, isothermal, because I didn't want to make it any more complicated than it has to be. And we have a Lattice-Boltzmann simulation and a lattice gas simulation. And what we see here is not even the shock wave, which works perfectly, but the collision operator itself. And if you look at, you have the pre-collision value and the post-collision value, and the lattice gas and the Lattice-Boltzmann do exactly the same thing. So what I claim we have shown here is that this is the lattice gas that underlies entropic Lattice-Boltzmann, which behaves exactly as entropic Lattice-Boltzmann would, except, of course, it's actually a lattice gas and has all the nice properties of being unconditionally stable and all that. It's as efficient as Lattice-Boltzmann and has all the fluctuations put in. Mm-hmm. Oh.
I'm just thinking, I've understood your viscosity right. That's the kinematic viscosity, and that should go like 1 over rho in a real gas.
Mm-hmm.
So if density times this kinematic viscosity is constant, then you make it actually got the right scale.
Yeah. I don't think it scales quite like that. I think we tried it. I think it scales a little bit differently, not just like that, because, yeah, there should be something else about the rarefaction of collisions. But yeah, it has exactly that effect. Yeah.
Casper Peterson, tell us about your fluctuation in lattice.
Thank you. I think I'm not gonna be as detailed as the other two speakers just before me, as I'm gonna start from a top-down approach with the so-called Fokker-Planck equation. But before I get into all my research, I'd just like to thank my funders and also my colleagues and, of course, my advisor, Professor Joshua Rinkerhoff. So what I will be talking about today is a little bit of like a brief motivation, a very overall motivation for why we should study thermal fluctuations, even though it was already prefaced in the previous two presentations. And then I'll talk a little bit about a lattice Fokker-Planck model I've derived. And then I'm not sure if it was right to call it simulations here, but I've done some initial numerical tests to see how this Fokker-Planck model can imitate noise. And so thermal noise, I think we've covered so far, is thermodynamic fluctuations are ubiquitous in in a lot of applications, and I started my PhD really focusing on phase transitions. So, for example, a problem like nucleation in boiling, and really in a case like this is quite complicated. You can look into a host of different physical phenomena, and one of them is thermal noise. So I wanted to, in my PhD, try to figure out how to model this with the LBM, but from a different perspective. Yeah, maybe this is a little bit, what do you say? Not basic, but anyways, the onset from the thermal fluctuations was that we want to be able to, at some point, go from a top-down perspective and correlate the thermodynamics to the thermal fluctuations, and essentially make it possible to simulate phase transitions on including metastability from a thermodynamic point of view, and at some point also consider, for example, the phase order parameter in the Hillard-Cook equation. You could, of course, as has been done in some other cases, just overlay the Brownian noise by brute force into your thermodynamics, but as I'll show in a bit, we do it a little bit differently. Yeah, this is just kind of an overview I tried to make of what has been done so far. We saw some very nice contributions that are very fundamental, but there's a couple of other ways to do it, and they mainly start with the so-called fluctuating hydrodynamics theory from Landau and Lifshitz, in addition to molecular dynamics, where you can get very fine resolution of tiny nuclei and phase transitions. But with fluctuating hydrodynamics, you can essentially add noise into your what's it called, your heat flux and your stress tensors, for example, and come up with fluctuating sources in either your Navier-Stokes equations in finite volume methods, or in the so-called fluctuating lattice-Boltzmann method with stochastic sources in the Boltzmann equation. And then you can also go further back and look at another approximation equation for thermal noise, which is the Fokker-Planck equation. And this was previously attempted to be used back in 2006 by, I have it here, Moroni et al., where they used it to, at least an initial simulation, to just do a simple cavity test. And that's about where I think they left off from then. Not more research had gone into a lattice-based Fokker-Planck equation. So that's kind of where I started with some of their work. So if we look at the Fokker-Planck equation, it's this probability distribution function that essentially recovers fluctuating Langevin dynamics, and it's composed of, this is probably the simplest model of a Fokker-Planck equation you can have, where you have an advection term here on the left-hand side, you have an acceleration term of your population F, and then on the right-hand side, you have essentially a drift term and a diffusion term, where really the stochasticity comes into play. And then in this Fokker-Planck equation, you set the strength of your noise really through the thermal speed. And in essence, this Fokker-Planck equation has the same equilibrium distribution as the Boltzmann equation. And so effectively what you're doing is imitating the Langevin dynamics for a single particle that gives some kind of Brownian stochastic sample path. You're trying to capture that now in an evolution equation like this in a probability setting, if you will. And so I essentially, in my PhD research for the last couple of years, I wanted to discretize this equation onto the lattice and really see if it can do a coarse-grained approximation of noise in kind of like so for example, this is just an arbitrary fluctuating field That is a very old test. But then the idea is that you essentially evolve your populations F in, for example, you're in the 2D case for your density or your total energy. And the core part of most of my work revolved around essentially using just Gauss-Hermite quadrature, good old Gauss-Hermite quadrature, to discretize, project our equation, the entire equation, onto the lattice. And it turned out that you can do that by carefully designing your Hermite coefficients, by essentially coming up with an eigenvalue property for your weight function. And it takes some extra tricks to essentially get to an expansion from the Hermite series here for the operator, but you can do it. It gets a little bit ugly, as I'll show in a second, but it's possible. And it was previously done for a simpler setting than what I've done, by, again, Moroni et al. Here, where they did this cavity test that I've talked about before, but they showed that the stability for the numerical scheme they used and this particular discretization was not the best. And it seems to also be the case in fluctuating lattice-Boltzmann methods that your thermal speed is really limited by the speed of sound as we see in normal LBMs. So kind of from a heuristic perspective, I wanted to bypass this and get some more stability into the scheme. So I ended up using particles on demand, actually. And that's why it got a little bit more hairy to come up with the Gauss-Hermite quadrature. So essentially in particles on demand, it's been explained previously in one of the, I think the previous sessions. What you do is you essentially take your normal peculiar velocity set here and you scale it by your non-ideal pressure from whatever equation of state you want, and I want to keep it simple. So I used the van der Waals equation of state, and essentially what you end up with when you use these kind of discrete velocities is you end up with really good stability characteristics, but you also end up with a very ugly operator when you expand it. And you also end up with essentially particles that need to stream from backwards in time to a current monitoring point from off-lattice sites, which makes the numerical solution strategy a little bit messy. But it's possible. And the operators, when you do your Gauss-Hermite quadrature, essentially end up looking something like this. They're just a series expansion again, and an approximation really of the Fokker-Planck operator. But you have your friction coefficient in here, and overall you have your thermal speeds. That's at your thermal noise strength, and then you also have your discrete velocities in here, and your hydrodynamic velocities along with the density and your momentum moment and your higher order moments. And should say that I also applied a double distribution function such that we can recover both the Navier-Stokes equation, but also the Fourier equation, an energy equation essentially. And to essentially integrate the lattice equation that we come up with in time, I wanted to keep it simple again, use trapezoidal integration. And normally with particles on demand, you need to do a semi-Lagrangian advection. But that seemed to be very difficult with the Fokker-Planck equation, just because it's a little bit more complex, I think. And in the end, what you want to do is you want to essentially reconstruct populations at departure points. And throughout their streaming from an off-lattice site to a current node that you're trying to update through the Fokker-Planck equation, you need to essentially reconstruct from the surrounding grid. And so you need some iterative procedure to essentially use a reconstruction stencil to correctly solve or predict these populations. So essentially, in a very simplified manner, what I do, it's a little bit of a heuristic and work in progress methodology. This is that you first perturb at the start of a time step, you perturb your populations within the stencil by the Fokker-Planck equation or by the Fokker-Planck operator as it's prescribed by trapezoidal integration. And then Pond, particles on demand, it uses this crucial step of transforming the populations in the stencil to the same inertial reference frame as the current monitoring point that you're trying to update. And so you construct essentially a transformation matrix that makes sure that your moments are conserved in either reference frame. And then you can essentially reconstruct with your preferred reconstruction kernel. And then we, again, a little bit heuristically, add the last part of the trapezoidal integration for our Fokker-Planck operator. And then we can essentially compute the moments for our density populations and also our total energy populations and iterate on this until our moments converge. And so with that, we kind of started making some very what do you say, some initial, I'd call them tests probably. And really what I've done so far is just start simple. It's very, very new results really. We've just started here with a lattice that's 128 by 128, normal D2Q9 with periodic BCs, boundary conditions, and we used Lagrange reconstruction to reconstruct these populations, and then just initialize with a Gaussian noise and an equilibrium population. And then really there's still some numerical details within this methodology and in the code that I've developed that are a little bit, that still need more development. So really these values for the van der Waals equation of state and the Fokker-Planck equation are a little bit arbitrary at this point. But in the end, I just wanted to show that that we can initialize this is just initialized with a Gaussian normal distribution. And then really what we want to look at is here the density, for example, and total energy and density. And what you'll see in these fluctuating fields is that there's some instability to start with. But in the end, it seems like you can evolve the fields with this sort of methodology. There's still a bunch of problems in it that needs to be ironed out. I need to figure out if the reconstruction schemes are conservative and come up with some better initialization schemes. And there's also seems to be some lattice pinning issues sometimes, but that could be because it's so non-uniform. And then you can also compute your hydrodynamic velocities. They fluctuate from your momentum moment. And I think that's the quick overview of what I've done with this work. So just to summarize, I used Gauss-Hermite quadrature and we've shown that it can be used to discretize the Fokker-Planck equation. And we developed a somewhat heuristic diffusion algorithm that's semi-Lagrangian that can evolve the lattice Fokker-Planck equation. And then we just started development of simulations. And for future work, it's essentially a lot of it's validation at this point to make sure that this scheme is actually thermodynamically consistent. And this requires both deriving fluctuation, dissipation theorems, figuring out if everything is conservative, and essentially figuring out good validation cases for noise. Yeah, I think that's about it. Thank you. Yeah.
So One point I didn't quite get, where does the noise come from? I mean, you have a continuous F which evolves under Fokker-Planck operator also continuously.
Mm.
When does it become noisy?
It becomes noisy from, well, it comes from that diffusion term in the end.
But that's still a continuous distribution, right?
Yeah, yeah, it is.
But there
That's
has to be
true.
some
Yeah.
sound procedure going on or something.
We still solve it as we still discretize the population and the operator, so it's technically not continuous. So it's recovered through essentially the diffusion term, the thermal noise.
But the diffusion term is, it's just a diffusion, it's not actually a noise term in the Fokker-Planck equation. There's a continuous evolution of the F, right?
Not to my understanding.
Okay, maybe I fully understand.
Yeah.
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 So when you're showing these fluctuations, essentially you know what from statistical mechanics the variance of the.
Yeah, you can find them. Yeah, you can find it. Yes, that's. Oh, I haven't gotten there yet. Just gotten the first fluctuation dissipation theorem, but you need to derive them all and then figuring out if it obeys the. Yeah, exactly. Yeah, still need to do that.
And I agree with Alexander, but when I looked into the 2006 paper, so we know that the Fokker-Planck collision operator has a basis of eigenfunctions that are the Hermite polynomials. So all that construction does is it gives you a Hermite MIT collision operator with particular numbers.
Yeah.
But the relaxation rates, and I've never seen why those numbers are better than any other numbers, just because they come from a Fokker-Planck collision operator. I've never seen the argument.
No. Yeah, I'm not sure what to say to that. Yeah, I think so.
Like a comment, but just to rephrase also the first question. I mean, my understanding from what you showed is that the noise is inside the initial condition.
Yes,
And
yeah, you have.
Gets propagated along time. Hopefully, supposedly, I guess, with the right statistics.
Yeah, yeah.
So, that's more of a comment, but just to rephrase.
Yeah. Yeah. Thank you. Thank you.
The other speakers, I think we have